Hi everyone, this is Sheida Shakeri. Today I'm going to present our research with my advisor, Dr. Ornek, which is titled Towards Robotic Fabrication in Landscape Architecture. Since the turn of the 20th century, the field of robotics has attracted the public's attention. Robots are programmed to perform certain behaviors and respond to commands to provide the user with helpful labor. Although robots are widely utilized in the industry, the technologies and solutions used in robotics are mostly not generic, but domain-specific. The industries that rely on manufacturing processes in which the workpieces can be moved around the manufacturing plant have benefited most from this technology. Recently, numerous design and construction disciplines have been transformed by the possibility of fabricating components directly from design information. Thus, robotic fabrication has become a hot issue of study in architecture. Architects use the capabilities of these tools to create complex designs that are challenging to manufacture by traditional methods. This approach opens up some new opportunities for innovative design explorations. Also, it is possible to modify and individualize architectural design and its materialization with minimal time and effort. Additionally, in the construction industry, architects use robots to deal with low productivity, lack of skilled workers, and high accident rates on job sites. On the other hand, when coming to the landscape architecture, due to the irregularity of natural terrains, they provide a high level of difficulty for digital fabrication. Besides, the on-site construction techniques and materials are tied closely to environmental factors such as ground stability, severe winds, and other factors. Therefore, robotic landscape modeling on the location needs to be flexible enough to adjust to these shifting environmental factors. And that is the main reason that it has lagged behind other fields like architecture and infrastructure engineering. The existing research on robotic landscapes includes planning and horizontal grading through the optimization of material flow with the use of GIS, suiting landscapes to local conditions by utilizing only on-site materials, developing a coastal design strategy for autonomous construction in dynamic environments, concentrating on local material changes for dynamic coastal defense, and using erosion and sedimentation's potential for forming landforms. Although the existing research on landscape robotics provide noteworthy developments, as you observe, they are limited in quantity. On the other hand, in architecture, there have been several research on the several aspects of the robotic fabrication. Therefore, we focused on the robotic fabrication and tools that are currently used in architecture to discover the potential and opportunities for robotic fabrication in landscape architecture. To do so, we conducted an extensive systematic review of the existing research and projects of the most renowned architectural institutions in the field of robotic fabrication. And a total number of 65 research projects were identified from 2012 to 2022. We classified and analyzed all the data under the themes of the use of material, the implemented task, the final product, and the project's goal. First, we sorted all category data chronologically, find the most and minor focus within years, and then we matched the final products with their goal and material in a separate Excel sheet. Extracted from the literature, architectural robotic fabrication goals were classified and analyzed into four main themes: productivity and efficiency, sustainability, safety, and new possibilities to construct things that we were unable previously. As you see, the proportion of studies with efficiency goals surpasses the others. Additionally, new possibilities and sustainability cover a large area of robotic applications. Yet, safety has been the mainly ignored goal. Also, with a detailed look, you will realize that efficiency had a slightly fluctuating trend, which experienced a sharp fall in 2021, followed by another fall in 2022. As the second most popular goal, the number of new possibilities has gradually declined after 2016, whereas it started growing again in 2022. Furthermore, although initially sustainability goals have increased enormously after 2017, finally, safety, which is the most ignored goal, has recently received little attention. Also, numerous tasks have been implemented in architectural robotics research and projects. The analysis shows that the most popular robotic task among architects is assembly. Though fluctuations in the number of assembly projects, the trend rose in 2019 and remained almost constant. Actually, this trend is not a surprise because robotic assembly is a critical phase in the workflow from design to construction, and the ultimate expression of a robotic fabrication system is in the assembly of the structure. Also, 3D printing and inside fabrication are among the most utilized tasks. In terms of utilized materials, the analyzed projects have shown great diversity. However, the most popular ones are timber, concrete, and brick. Looking in the chart, you will realize that although timber covers a large proportion of the materials, it has been ignored until 2014. Yet it is the most in-demand material in recent years. Notwithstanding the concrete and timber, brick has received the proper attention from the beginning of the period. However, it has lost its initial popularity in recent years. The review of the implemented projects provide various products in structures, pavilions, facades, mesh mold, floating objects, sculpture, robots, tools, and frameworks. However, since 2013, structures have been the most popular products. To clarify, structures include footbridges, slabs, frames, and walls. Then, pavilions and tools are the second most popular robotic products, covering almost one-third of all. To explain, tools cover novel fabrication processes, construction platforms, and design software. As an additional step, a separate Excel sheet was created to match the most popular products with their extensively used materials and goals. The popular products were extracted in the previous step as structures and pavilions. Tools and frameworks were excluded from the product category because they mostly do not contain any materials. As you see, structures mainly utilize concrete and timber for productivity, efficiency, and safety purposes, while pavilions involve a wider variety of objectives: sustainability, new possibilities, and safety. Fiber-reinforced composites are the most significant materials that are used in pavilions. Finally, we summarize all the variables based on their most popular attributes for each year, which shows that the sustainability goal as an essential element in the landscape architecture has been prioritized in recent years. Shifting to the task part, the most common tasks in architectural robotic fabrication include assembly, 3D printing, and inside fabrication. While assembly and 3D printing maintain an increasing use, inside fabrication tasks have decreased recently. This fact also highlights why the on-site robotic fabrication of landscape architecture cannot go beyond the automation of the existing techniques. Additionally, 3D printing as an essential task in architectural robotics faces boundaries in the realm of landscape architecture because of the large scale areas. Due to the financial and physical limitations, current 3D printing technology cannot support such situations. Coming to the architectural robotics' most prevalent materials, sustainable and unsustainable resources were both used. Even the allocation amount of sustainable materials varies. While more conventional types of sustainable materials like timber have been widely used, materials like fiber composites and biocomposites are less employed. As a result of analyzing the robotic applications in the field of architecture to examine the possibilities it can offer to landscape architecture, the research spotted both the gradual and sharp chronological changes in each theme, Also, we could discover the correlation between the subjects and highlight the gaps and opportunities in the realm of robotic landscapes. Yet, the scope of the research is constrained in terms of comprehensiveness of the research labs. As a future step, we plan to collect more projects from different research groups and increase our dataset. These are the references that are used in our paper. Thanks for your time and attention.